So what we're going to do today is continue talking about some of the features in Android Linux kernel. And in particular, we're going to talk about the local and remote interprocess communication mechanisms. And I'll also talk a bit about how Android Linux provides processes and threads, which are used to mediate access to one or more processor cores. This will, to some extent, be a foreshadowing of what we'll be covering next semester in the next course I'll be teaching. So hopefully, if you like this course, you'll consider taking that one, which will be cool. And it'll give a much deeper understanding of all the foundational concurrency and synchronization mechanisms you're likely to run across with Java. So what is interprocess communication? Well, as the name implies, especially if you've taken an operating systems course, interprocess communication, or IPC, is a set of mechanisms for allowing interactions between processes that are running in, or threads that are running in processes which may or may not be on the same machine or may be split across a network. So it's really communication between processes. In Android, it's typically used to communicate from one app to another or from an app to some system services or vice versa. And as we'll see, IPC is an essential part of mobile cloud computing for clients. So clients need to do stuff that will allow them to send data to either other processes on the same machine or more likely some server out in the cloud somewhere. And obviously there's a server side to all this as well, which is the part that takes the request from the client, does some processing, and then ships the results back to the client. So we're not going to go into a lot of detail here on IPC other than just to tell you sort of the mechanisms that Android Linux provides you to do this stuff. That is a great topic in its own right, and if you're interested in it, the MOOC I have on Android app development will go into a lot more detail about this stuff. There's a bunch of different IPC mechanisms that Android Linux provides. Not surprisingly, the first and foremost is the TCP/IP internet stack. So you're undoubtedly all familiar with that in one way or another. And that's how you communicate from your Android device over to a server somewhere in the cloud. And that uses the transmission control protocol and the internet protocol and so on in order to be able to make byte stream, reliable, two-way communication. This is, of course, optimized for local area networks and wide area networks. Typically, in a mobile cloud computing environment, you'll be talking to things over a wide area network because the services typically reside somewhere out in the cloud. Android Linux also supports something called Unix domain sockets, which are sometimes called local sockets, which are used or kind of optimized for communication between processes on the same device. So you might have some app that's running, like you might have the browser, Chrome browser, running on your phone, and it needs to be able to talk to the window manager, and so it'll use some kind of local socket or Unix domain socket buffer to communicate from one address space to the other. And this particular protocol is optimized for intra-host interprocess communication. And all that just means is when the processes run on your mobile computing device, that's typically using, for some things, it's using Unix domain sockets. There's also something, and I should mention that TCP/IP and Unix domain sockets are pretty standard. That's good old Linux stuff. TCP, of course, is broader than Linux. It'll work on Windows and VxWorks and Mac OS and anything else. Unix domain sockets, you're not going to find them on Windows per se, but you'll find them other versions of Unix. But then there's also something else called the binder driver. And this is intended to support message-oriented interprocess communication as opposed to byte stream-oriented communication. So both TCP and Unix domain sockets are so-called byte streams, which means that the protocol itself doesn't obey message boundaries. It's up to you, the developer of the applications or the services, to figure out how to chunk up the stream of bytes into records or messages, whatever that might be for your purposes. And so the binder driver, however, does message-oriented interprocess communication. And this is not standard. You won't find this on other versions of Unix, but it is something that Android uses very heavily. And it's supported by a device driver that runs in the OS kernel. So basically, the reason for doing this is twofold. Number one, they wanted to really optimize sending large chunks of data around, and they do it in a very clever way where they actually can pass pointers and then put the data into shared memory. So that's one reason. So it's optimized. It's also just optimized because it supports message orientation by not requiring the application or the services to have to manage the message boundaries as much. And we'll talk in a second how that works under the hood. Underneath the covers, the way this all is implemented in the operating system is with something called the device driver framework. Linux, Unix, Windows, everybody has a device driver framework, which is basically a way of plugging in code to handle various hardware devices. So you'll have hardware devices, things like network interfaces or flash memory controllers, things that actually talk physically to the hardware, and that's in the hardware space. And then in the operating system kernel space, there are these device controllers that are software that are managed through things called device drivers, which are basically little pieces of kernel code or code that run in the kernel that do basic operations that interact with the hardware. And they're typically very simple. They're things like open, close, read, write, select, ioctl, and so on. So there's just a handful of these methods that handle all the low-level details. They're block-oriented devices that transfer data in chunks. This is typically for things like file access. There's also character-oriented devices that transfer the data sort of in a byte stream or byte by byte. These are typically things like network protocols or other kinds of touch devices. And the whole purpose of having this layer in the kernel is so that you don't have to worry about this stuff, or more importantly, the operating system that lives on top of this device driver framework doesn't have to know or care about low-level details. And that allows the hardware to be accessed more securely because the kernel and the device driver framework manages the security and permissions robustly. If something goes wrong, then hopefully there's a way to recover from it. And portably, you can write code. Actually, this code in the device driver level is usually typically very device-specific, but the higher-level applications don't know and don't care how these things actually behave. So you could have different types of network interfaces, all of which are accessed through the portable socket layer. Programming at this layer is really hard. You have to have low-level knowledge of things like kernel debugging, which is really tricky, and also just low-level knowledges of languages like C and things like interrupt handling and all this good stuff. So it's not for the faint of heart. And the good news is very few people ever have to write this code because it's handled for you by people who do things in the kernel, and then we leverage everything that runs on top of that. I won't say much more about this. There are definitely places to go to learn more about this kind of programming, but for the most part, the only people who would need to know this would be folks at OEMs of Android hardware. So if you worked for Samsung or LG or HTC or Motorola or whoever else is selling Android devices today, that would be someone who would need to know that. But the average application developer goes nowhere near this stuff. The next thing I'd like to do is talk a little bit about processes and threads. Again, I'm assuming you've gotten a lot of this stuff in the operating systems course, but I'll just give you a quick recap. And as I said before, this provides a nice interaction or a nice intersection with what we'll be covering next semester, because it is what is provided in the Java virtual machine atop what we're about to discuss, although it doesn't necessarily have to be Android. So there's support for processes and threads. Here's how we kind of draw these things. I'll talk more about what the icons mean here in just a second. The purposes of having processes and threads is to be able to, in the operating system kernel, is to be able to encapsulate application instructions and the data in a way that's efficient, reliable, and secure so that the actual processing can be done on one or more of the processing cores. So the diagram here shows the little gray round angle. We have two examples of them. We have, say, a browser and an email app, and those are running in separate processes. You can see these little funky things here. They look like little stacks. Those are the threads. And so you might have multiple threads running around in this process. You might have several threads running in process B, several threads running in process A. And as we'll see shortly, the threads actually can be mapped down to the underlying processor cores. So why the heck do people do things like this? Well, the process provides a unit of resource allocation and protection. And what that really means is that if you're running within a process, if you're a thread running within a process, then you can't muck with the internal state, or instructions for that matter, of other apps running in other processes. It's basically fenced off, and it's fenced off by something called a memory management unit, or an MMU. So So there's really no way for something in this process, say the browser process, to go and screw around with the phone process or the process running the phone app or the process running the email app. And each app in Android typically runs in its own Linux process. There's sort of ways around that, but that's a good way to think about it. If one app crashes, that shouldn't affect the other apps because they're not really sharing anything directly. If they're sharing anything, it's through inter-process communication mechanisms. So it makes your systems more resilient. The data in each of the apps is private, so this process can't stomp on that process's data. And by default, every Linux process starts with one thread, which is typically the main thread, or in Android terms would be called the user interface thread, or the UI thread. And you can read more about that here at the Android documentation. What this thread does in Android in the apps is it typically is used to run the event loop that waits for things to happen, like touch events or network events or whatnot, and it then dispatches the events to various widgets and components that are provided by the Android user interface toolkit. So components in the Android user interface toolkit know how to handle events that are dispatched to them by the event loop in Android. And it's a little bit beyond the scope, well, it's way beyond the scope of this class because we're almost done, to talk much about how Android's designed internally, but we'll talk about that a little bit next semester. And if you're really curious, you can always go watch the videos from the MOOCs that I've done that go through this in more detail. A couple things real quick. You might think this is sort of obvious. Well, what's maybe not so obvious is that back when people first developed phone operating systems like what we were talking about the other day, the Motorola P2K operating system from back in the day, they didn't have these distinctions between apps running in separate processes. So if one app went berserk, it screwed up the data and the instructions that the other apps were using because they were all running in a common address space, which was, of course, a horrible debugging nightmare. Threads, which of course are the foundations for all the concurrency stuff we've been talking about and parallelism stuff we've talked about in this class, can appear at multiple layers in Android's software stack. So we've got some stuff down at the operating system kernel level, the so-called kernel threads. We also have things up in the POSIX, in the native libraries level. So we have these so-called POSIX threads, which are really little facades around the kernel threads. Java itself and Android's runtime environment, its virtual machine, and so on, have these VM threads. And then there's also Java threads, which are what we've been talking about, to the extent we've talked about threading in this class, which has been a very small amount of time. The Java threads were the things that we were focusing on. So you can see there's threading all over the place. And the way it works typically is a Java thread is implemented on top of an Android VM thread, which is implemented on top of the POSIX threads, which are implemented on top of the kernel threads in Android Linux, which ultimately interact with the hardware. So that's basically how the different pieces interact. Obviously, we're going to focus on the kernel threads here. So let's talk a little bit more about threads and processes. It's kind of important to understand this, at least at a high level, or at least enough to be able to answer the questions on the next quiz. So threads provide units of execution for streams of instructions that run on the underlying processor cores. So the processor cores are what's actually doing the work, and the threads are a software-enabled abstraction to access those underlying processor cores. And so by default, as we said before, a Linux process has a single thread. You can create more threads if you want to, and obviously there are different ways to do that. If you're programming in Android, you're probably going to use the Java Thread API to do that, although if you're programming the lower layers, like the native development kit layers or the system services layers, you could make calls to the POSIX pthread API directly. Threads can run concurrently on one core. So if you had the misfortune of having an old Android device that only had one processor core, then all the threads would be multiplexed on top of that one processor core, which would work, and that's the way it used to be. But nowadays, as I mentioned, more and more systems have multiple cores. And so in those environments, then the threads that are at the application level, or the system level for that matter, can be multiplexed over a larger number of processor cores. And so, in fact, they could run in parallel. And if you use some of the abstractions we've been talking about in this class, like parallel streams and completable futures and the fork join pool and so on, as you undoubtedly noticed if you ran the emulator very much for the assignments, they do in fact run in parallel. And that's why the versions that are fork join pool, parallel streams, completable futures give you a much bigger boost in terms of performance versus the single-threaded solution. So if you run your emulator with the single-threaded version, you see it takes a really long time because it's doing everything sequentially. Whereas if you do it with the other versions and you have a multi-core machine, it'll run a lot faster. All right, some other things that are important to know, at least at a high enough level to regurgitate on a quiz. Each thread has certain unique resources. So each thread has its own stack. That's what this icon is trying to represent, little stack. Each thread has its own program counter, which hopefully you remember from your computer systems organization course is what's used to keep track of the next instruction in the stream of instructions to execute. They also have other registers, things like the frame pointer and registers to do operations and computations in, and so on and so forth. These are all unique resources. Each thread has its own copy of this stuff. There are also certain resources that are shared across other threads within a process. Now, these resources are not shared by other threads and other processes, but they're shared with threads in a given process. So some examples would be open files or open sockets, memory, like the heap. Those are all things that can be shared within a process by the threads in that process. If you want more advanced sharing with things like Android shared memory, that takes extra work. It's doable, just extra work. So the Android Linux kernel, just to show you the visualization. So this is the sort of the low-level view. The Android kernel threads basically provide a foundation for the Java threads in Android's middleware architecture. And that is not an Android-centric way of doing things. Pretty much every Java virtual machine is implemented by taking the Java threading abstractions and then layering them on top of the underlying operating system kernel threads, or more likely the C language library interface to the kernel threads. So if you look at the Java platform you would get out of the box, it'll then implement the threading abstraction in the Java layer with P threads or Windows threads or whatever. So again, you can find out more information here at this link. Processes and threads consume non-trivial amounts of system resources. Now, these days, not such a big deal, right? If you've got plenty of memory, as most modern smartphones do, certainly most modern laptops and servers do. If you have plenty of cores, not the end of the world to have a bunch of these things. But you can't just spawn, thousands and thousands of processes or threads, because if you do, your system will start to bog down. Moreover, it's often, as we've discussed a number of times, it's overkill to have too many threads. It really makes sense to use threads for operations where they're going to run for a while. And if you recall our discussion we had about a month ago when we were talking about the N times Q model, and we talked about the number of threads you need to have in your processor pool, your thread pool, in order to be able to have things be efficient and responsive, you know that just spawning a thread for every piece of work is probably not the best way to go. So it's much better to typically much better to have a pool of these threads that get shared. So the only point here is just don't get too carried away with this. You'll regret it if you get over-exuberant in your creation of threads. Programming multi-threaded apps can also be hard. Hopefully the thing that you've learned from this class is if you use the right level of abstraction, like the Java 8 parallel streams or completable futures frameworks, it's easier to build parallel and concurrent apps, because those frameworks shield you from a lot of the low-level details, especially things having to do with sharing resources between threads. If there's one thing I want you to remember from this class is if you arrange your processing abstractions correctly using the proper frameworks, all the low-level accidental and inherent complexities of sharing resources between threads basically go away. So, we could do pretty much this entire course without ever having to talk about synchronization at all. And that's because the mechanisms that we provided using parallel streams and completable futures shielded you from those details. What we will talk about next semester will be concurrency and synchronization mechanisms for the cases where you have to share resources between threads. And it turns out that there's plenty of cases where you actually have to share stuff, where sharing or not sharing is not an option. You've got to share. So in that case, you'd have to have a deeper understanding of synchronization and other forms of coordination. So that'll be next semester's topic, but you can get a pretty long way in life just by understanding the parallel computing APIs. Some of the problems, we've talked about this before. You'll learn a lot more about this next semester. Race conditions, where you have multiple threads accessing shared mutable state without using the proper locks, which causes chaos and insanity. And of course, deadlock is another tricky issue. So designing software that won't end up with a deadly embrace, a circular weight, can be hard, especially if you're doing it in a very free-form way. And especially if you're doing it with object-oriented programming environments where you have callbacks, which get really tricky to do with, without running into deadlock. So how do you deal with this? You got to learn to think deeply about these things. First line of defense is just not to have shared mutable state at all, if you can get away with that. But if you have to learn about the synchronization and concurrency mechanisms. Probably not a bad idea to read the Android documentation if you're using Android, or more generally reading the classic books and literature on the fields, especially things like Concurrent Programming in Java, which is an excellent book. There's other books as well. And I've got tons and tons of stuff on my website above and beyond what we've covered here if you're curious. So you can go here and learn way, way more stuff than we have had a chance to talk about. Again, just to reiterate, I'm a huge fan of using higher-level frameworks because they shield us from the low-level details of all these accidental complexities. OK, so that's the end of that discussion.